In part 4 of section 14, we're going to be discussing the end behavior of a polynomial function. This will be the last major piece to the puzzle that we need in order to successfully graph a polynomial function with the degree of accuracy that is required of a algebra class. Definition 14.2 is going to do two things for us. It's going to tell us what the end behavior is supposed to be, and it's also going to give us some notation to help us with describing the end behavior. So it starts with saying the end behavior of a polynomial function f is, so let me highlight this, end behavior of a polynomial function f is a description of what happens to y values as x values become large. Now there's two ways for x values to get large. They can get large in the positive direction, or they can get large in the negative direction. When we think about the x-axis, the x-axis is a place for us to reference the x values in a Cartesian coordinate plane. So on the x-axis, we only get to see a certain amount of the axis. So looking here at example 14.8, just as a reference, I certainly see the numbers 1, 2, 3, 4, and so on, but if I was to continue to go out here to the right, I would go beyond the window and I would be heading in the direction of positive infinity. So even though the window isn't big enough to be able to actually represent positive infinity, there is a very well-known direction for where that is. That would be what we're talking about when we say the x values become large. X values become large as we go off of the window and head toward infinity. Now that can also be done going off the window to the left, which would head us in the direction of negative infinity. It's still x values getting larger, they're just getting larger in the negative direction. So we use the infinity symbols not to represent a real number, but just to represent the notion that we're going to be getting very, very large. So anytime the domain of our function is negative infinity to infinity, which is precisely what we're going to have with a polynomial, then we get to do the following. We get to say x arrow infinity means x values become large in the positive direction. And the counter to that would be x arrow negative infinity. This means that the x values become large in the negative direction. Now, we don't typically say x arrow infinity, x arrow negative infinity. That's just the name of the symbol. But the symbol actually has a English translation. The arrow that you see here actually represents the word approach, or really approaches. So we would say x approaches negative infinity. So this is a way for us to describe the x values are going to be getting very large in either the negative infinity direction or the positive infinity direction. So we're going to use that as a means to describe the end behavior of our graph. So the end behavior of the graph is represented by the arrows from the curve that are going off the window. So each one of these pictures has two arrows, one that's on the right-hand side and one that's on the left-hand side. So we're going to write a statement to go with each arrow describing where we are going off of the window. Now the reason why we do this is because it is impossible for us to have a window big enough to have the entire function graphed. The graph is going to always be so large that at some point we have to put arrows to indicate that it's going to continue to go off of the window. We just can't make a window large enough. So we use the end behavior as a way of describing precisely where we're going to be going off of the graph. So there's a general structure to making these statements. We say y approaches something as x approaches infinity. So when we say x approaches infinity, we're talking about the right-hand side of this graph. There is an arrow associated with the right-hand side of this graph. That would be this arrow up here at the top right. This is going to be what I'm going to call in behavior number 1. And we'll call this statement number 1, just to be able to match them up. And that arrow, while it looks like it is going up, but it's not going up completely vertically. It's going up, and it's also going a little bit to the right at the same time. It's going up and to the right. Now, it's certainly going up faster than it's going to the right, but it's not just going up. So this is what we call the right-hand side in behavior. So since the arrow is going up in the y direction, we can think of the y-axis also as having a positive infinity, and down at the end having a negative infinity at the bottom. So the y value, because of the arrow, is heading in the direction of positive infinity, and then also because of the direction of this arrow, the x value would also be heading toward positive infinity. A second statement can be made that will mimic this for the arrow that's on the left-hand side. This is the left-hand side in behavior. Again, the general structure is we say y approaches something as x approaches negative infinity. X approaching negative infinity means we're talking about the left-hand side of the graph. So for the left-hand side of the graph, we can see that the arrow is going both down and to the left at the same time. It's not completely vertically straight down, but it is going to the left a little bit as well. So we would say that y is approaching negative infinity as x approaches negative infinity as well. Let's try this with part B. We have the polynomial g graphed here, and I'm going to label the right-hand side arrow as number 1, the left-hand side arrow is number 2, and we're going to write down the general structure for our in behavior statements. That'll be y approaches something as x approaches infinity. We always do that for the right-hand side. And then we'll have y approaches something as x approaches negative infinity, and that's what we always do for the left-hand side arrow. Then all we have to do is determine what is the y direction for the arrow. Since both of these are going up, I would say that they both are going to say y approaches infinity, and that would be as x approaches infinity and also as x approaches negative infinity. And finally, for part C, we have an arrow on the right side down here toward the bottom, and then we have an arrow on the left side up here toward the top. So just by realizing that, you'll already have an indication as to how the statement should be written. But I always like to write it as just sort of a general skeleton first. We have y approaches something as x approaches infinity, and then y is going to approach something as x approaches negative infinity. So for the first statement, we can see that the arrow is going down. So I would say y approaches negative infinity. And then for statement 2, the arrow is going up. So y is going to be approaching positive infinity as x approaches negative infinity. Now what we've done here is taken the picture of a graph, and we have written statements about the in behavior from looking at the graph. But ideally, what we would like to be able to do is just look at the equation and then use the equation to be able to write the two limit statements or the two in behavior statements. And then the in behavior statements would eventually lead us to helping with the graph. So we don't want it to be graph turns into in behavior statements. We want it to be in behavior statements turn into the graph. So for example 14.8, this gives us an introduction into the idea of in behavior. You'll want to make sure that you go on to theorem 14.3 and example 14.9 so you can see how we can do the exact same thing, but we're coming from a equation to get to the statements that will eventually lead us to the graph.